I'd first of all like to thank you all for coming. I'm really, really very pleased to welcome everyone to this event for our G.O.L.D alumni. G.O.L.D alumni, the G.O.L.D, the acronym G.O.L.D stands for Graduates of the Last Decade. So it's really the gold that we, blue and gold. So these are, the true blues are from beyond the past decade. And so don't worry, if you're not in the past decade like me, it's not, so I'm especially pleased to mark the collaboration between Berkeley Engineering and our generous host at Google. And without too much of a preamble, I think you're really here to have a really sort of wonderful interactive panel discussion with a wonderful panel here in these directed chairs. And the question we have posed is, you all hear about how IT is part of the problem in terms of energy consumption. But really, today, we want to ask, can IT innovation solve the energy challenge? And I think it's especially arcane to the folks here because, as I think you'll see during this discussion, there's a huge amount that the methods of information technology, the methods of computer science, methods of electrical engineering, computer science, and really can be melded with more traditional approaches. Sure, there's biofuels and there's wonderful materials and PV, and those are all part of the solution, but it's really the methodology that we have, there's a lot to offer. So anyhow, without further ado, I'm going to introduce them in the order that I have written here, which doesn't correspond to, but I think I know where everybody is. So Peter Norvig. Peter is Google's Director of Research. He's a Berkeley PhD. Peter is known for his work in AI and, of course, the book with Stuart Russell and natural language processing amongst his many accomplishments, including our Distinguished Alumnus Award last year. Luiz Barroso, distinguished engineer at Google, where his interests range from the design of Google's computing platform to energy efficiency and power provisioning. From Berkeley Engineering, we have Randy Katz, who's out there, one of several key faculty members associated with the RAD Lab, which brings together partners Google, Microsoft, and Sun to develop technologies for large-scale computing efforts. Reliable, adaptive, distributed computing, that's what RAD stands for. And finally, we have Professor Costas Spanos, who during the time, he's currently Associate Chair for ECS, but he was till recently the Associate Dean for Research. And he really helped develop a lot of the strategy for the kinds of energy-related research that we do in Berkeley Engineering. And just to give you a sense, we thought we'd have Costas just do a few slides to sort of set the stage for the panel discussion. So just a few slides. No, he won't snow you with PowerPoint. And then all the other panelists have graciously accepted to sort of, we'll have a little bit of an interactive discussion. I'll start off asking him a few questions and then really throw it open to you to have a discussion. So really this is the format is to be in the format of a town hall meeting. So Sanita, if we can get you and Costas. So let me introduce Costas to get us started.
All right. Well, thank you. Thank you very much. Just a couple of slides, most of them not mine. But the theme for tonight, the question for tonight is, can IT innovation solve the energy challenge? And the answer, of course, I personally believe it's a strong yes. And I hope you will see that reflected in the discussion. We would like to bring 3 examples on where this can make a difference in buildings, in distribution, and in computing. Just an example from my colleague, David Kaller from UC Berkeley, where what you see here is when we try to solve the problem of green buildings, the greenest building in campus, at least in appearance, is Soda Hall, the computer science building, as you can see over there. But if you monitor its power consumption, which is relatively easy to do, without even disaggregating the power consumption at all, you will see that the load is built out of servers, building support systems, plug loads, HVAC, and lighting. What is really, I think, problematic and what presents a huge and hopefully low-hanging fruit is the fact that the duty cycle on a 24-hour basis doesn't really go very deep. In other words, the building consumes as much power during the day when it is fully occupied as it consumes at 3 o'clock in the morning on a Saturday when almost nobody is there. And that presents some opportunities, I think. Extending these opportunities on the scale of the whole Berkeley campus, you can see here the consumption in terms of kilowatt hours per square foot, or the total consumption. Each dot corresponds to a building in the campus. It's a large diversity going from buildings that are just built or buildings that are 100 years old or more. And you can see that there is a huge spread. Smaller buildings are actually more efficient than bigger buildings. And it might be almost embarrassing to admit that some of the newer buildings are actually not efficient at all. Again, we view this as an opportunity, and we are signing up to use the campus as a test bed where we use information technology to reduce its footprint dramatically. The idea, of course, is to monitor, model, and mitigate. Monitor, we'll say a few things about. Model, of course, is to try to understand where the energy is going. And most importantly, what controls its consumption and what improves its efficiency. And of course, the mitigation is all the clever things that we have to do in order to reduce its consumption and reduce the carbon footprint. And this is a little snapshot here of a fairly detailed measurement of a corner of soda hall when you disaggregate all the plug-in loads and everything else using a sensor network. And then you try to use this information to build a model to generate the appropriate community feedback, the appropriate supervisory control, and maybe even the appropriate automatic control for the building systems to get the job done. And another low-hanging fruit, this is not from commercial buildings, but this is from residential places where what you see here is 10 identical residences occupied by people with the same demographics. And you can see the power consumption in each area. That tells us that the power consumption depends quite a bit on occupant behavior, and that perhaps represents another big opportunity to get things done. So how do you exploit this? This is an idea from my friends at MIT, and I wouldn't bring it here if I thought it was a great idea, but it's an interesting idea nevertheless. What you see here has a diameter of about this big. It is called the Thigh Master, and maybe you can start guessing what it is. You can see these interesting prongs coming in. The idea is you wear it in your leg. And if your power consumption exceeds a certain limit, it makes you feel really bad about it. They actually spend research money to do this. I actually do not think that this solution is going to work for most of us, but there are other solutions. Information technology can really make a difference because, as people say, and I'm sure in this company it's pretty well understood, you cannot impact something unless you monitor it. Unless you don't know what it is, you cannot do anything about it. So this is an idea about using pervasive energy monitoring in a home and distributing. It is working, and distributing the information, disaggregating the information to the different home components, and having the information available to you. Of course, that dovetails very nicely to the Google Energy Meter. And if you're still signing up beta users, I'll be glad to sign up if that's available. Again, you cannot improve something unless you can measure it. And I think that information technology can play a big role in mitigating occupant behavior just by making the energy consumption visible. Moving on to the next challenge, to the distribution of energy, and this is one of the slides that I stole from my colleague Randy Katz and some other friends at UC Berkeley. What this slide says is that when you start now expanding the scale down to the national scale, perhaps, and you try to take advantage of energy sources that are not polluting, like sun and wind and so on, well, it so happens that these resources are not at the same places where the populations are. This is, for example, where the solar power exists. This is where wind power exists, and of course, this is where the population is. So you have to figure a way to take this energy and distribute it to the appropriate places, and that gives us an opportunity and a challenge to rethink the way you distribute energy and maybe create a grid that takes advantage of information technology and takes advantage of 21st century ideas. This is a slide that is directly stolen from Randy Katz, and he has much more to say about that. But I just wanted to mention that when you start dealing with energy the same way that we very successfully dealt with information and the distribution of information, where the distribution can be locally unreliable, but in the aggregate very reliable because quite a bit of redundancy, and also optimized because now you're going to be distributing energy based on information that is going back and forth. And this is an architecture that I believe it is dramatically different than what exists today. It is very scalable. You can have this architecture where you have this intelligent power switch that monitors supply and demand and decides when to buy or to sell energy in packets. This can be done within appliances, within homes, within communities, within towns, and so on. Finally, challenge number 3. Information technology, of course, is going to be part of the solution because it's going to give us the information that we need to do something about it. But information technology itself can improve its own footprint quite dramatically. The idea here, letting IT lead the way by example, is to look at the low-hanging fruits here. This slide tells you about the fact that computing today is not proportional. What it means, and maybe you can look at this one first. This one gives you the states in terms of density, how much time a CPU spends being utilized 100%, how much time is spent being utilized about 35%, and how much time is spent being idle. And as you can see, CPUs spend quite a bit of time being there in this typical operating region. And that would not be a problem, except the power consumption, and when you see in this green line here, really does not scale all the way down to 0. It scales all the way to 50%. So when you spend your time here, you're being very inefficient because you're utilizing quite a bit of energy for doing a little bit of work. So the mantra that we keep repeating to ourselves is about doing nothing well. The emphasis is on the well. We want to make sure that when we do nothing, we do not waste energy. And that's one of the ideas, of course, is energy proportional computing. Energy flows in the data centers. Randy Katz kind of opened my eyes to the fact that computing is really a big industry in the sense of sheer physical size. And when you see square miles and square miles of servers, and of course, this has many implications. Servers do not only compute the power to do the computing by switching transistors, but there's quite a bit of ancillary power in order to keep them cool, in order to keep them organized and controlled and so on. And you can see the breakdown on how this power breaks down. So there's quite a bit of opportunity there. If energy proportional computing takes hold and is applied in a massive scale, it's going to make a huge difference. Okay, so just to close, 3 opportunities where IT can make a difference: buildings and energy, collecting enough information, making it available to the people in the appropriate format, and giving them the tools to do something about it. Not only giving the tools to the people to do something about it, but also automating some of that. Many of the consumers in your homes are not people, they are appliances and so on. Intelligent grids, managing the distribution of energy, using ideas that we learned in the last 20 years on how to manage the distribution of information. Do it in a very scalable way and flexible way. And finally, proportional computing at data centers, and I'm not going to say much more about it because we really have the true experts sitting over there on the other side of the podium. I do have to say, however, that when you go in the whole hierarchy, there is quite a bit to be done at the bottom. When you actually make the transistors and make the computational elements that do the switchings and the ones and zeros, there are dramatic opportunities there to reduce the energy required for that fundamentally by maybe a couple of orders of magnitude by using transistors that depend on tunneling and so on. And there is quite a bit of exciting work there as well, in addition to the higher levels. In closing, and I see Shankar wants to get me off the stage, this is a nice view that up from Berkeley Hills, and that reminds us that that's a problem worth solving. So I hope that we can get a good discussion about it today. Thank you.
Thank you, Costas. And while you folks are getting warmed up to engage our panel, I'll just get them started a little bit. And if you'll allow me, I'd like to get them a chance to say a few words. And so if I could start with Peter. Peter, how can we give people better information to allow them to improve residential energy usage?
Okay, I think that's a good question. You know, we in the slides here we saw the more large-scale or commercial usage, and I think there is a lot to be done there. But of course, that's harder. You got to retrofit buildings and so on. Another place to attack is for the consumer, and we saw a little bit about that. And we've taken a similar approach of we have a project called the Smart Meter, of being able to put a meter into the home to get a better handle on where your energy usage is going. And we find that consumers are able to reduce their usage by about 10 or 15% just by being aware of it. And we didn't even have to put any sharp spikes into the thighs to get people to do that. And this is starting out really just at the beginning, right? Because this is just, you get a little readout and you say, aha, you know, all my usage is going to my refrigerator or my lights or something. You know, what change can I do to fix that? But so far that's just an individual looking at it, and we think there's a lot of opportunity for sharing as well, to be able to say, you know, what other people are like me with similar loads. We saw a chart there where there was a twofold difference between similar households. If you can not just look at your own data, but say aggregate over lots of people and then say, now how do I get myself from above the blue line to below the blue line? I think there's a lot of value in sharing that kind of information.
Luiz, Google's operations are naturally pretty energy intensive. What's Google doing to make its data centers more energy efficient?
Thank you. That's a very timely question, since we happen to actually have released quite a bit of additional information about that over the past week or so. If you search at Google for efficient data centers, you're going to find a page that actually has a bunch of data for a summit we ran last week on Wednesday, unfortunately on April 1st, but
that wasn't the plan?
It wasn't. I don't think it was officially the plan, but you know, somehow we still had enough credibility that people believed that it was either going to be true or entertaining, so they showed up. And it was a summit that had people from a lot of different representations in the industry, other companies like Amazon and eBay, industry groups like the Green Grid were present as well. So anyway, it was a summit to talk about energy efficiency in the context of best practices, not necessarily focusing on what is the next crazy technology that's going to solve that problem, but instead, what can we do with technologies that are available and inexpensive sort of today to make data centers much more efficient than they are. So I'll sort of summarize very quickly the state of the art in that area and some of the key things we talked about, just to tease you to ask me a few questions, and I'll tell you more later if that's the case. But basically, there's this general impression across the industry, and some studies to back it up, that data centers actually waste about, twice as much energy as it's actually fed to computers, right? That's a measure called PUE that's fairly standard in the industry right now, in which you take all the energy that enters the building and divides by the energy that's actually given to computers and networking switches and things like that, right? And if that number is 1, you're perfectly efficient. If that number is greater than 1, you're wasting something, right? So the typical data center out there is probably above 2, but the ones that actually dare to measure are probably averaging sort of around 2. And that's when you hear things, people saying that a watt is wasted on cooling and power distribution, et cetera, for every watt that's actually used for computing. That's what that is, that PUE of 2. And we've disclosed a while back that our data centers actually work on an average that's actually, wastes 1/5 of that amount of energy. So our PUE number, instead of being 2, is actually closer to 1.2. In fact, I think that the latest number is 1.19, which, if you're sort of in this industry, you probably recognize that that's a really, really ambitious sort of number. And the fact that this is not sort of a demonstration prototype, but it's actually the average of all our Google designed data centers, it's actually, in my view, sort of really impressive. And not only that demonstrates what can be achieved, that it can cut waste by a factor of 5, but also we were able to talk about how we actually did that. So there's a lot of things we did in the power distribution and in the way we cooled data centers, some tricks that had to do with how we actually design our servers as well. And none of these things are sort of, crazy technology that maybe is going to be affordable in 5 years, right? Clearly, we're a business that turns a profit. And we do that because it's sort of good for our business as well. So the fact that we were able to demonstrate those numbers and actually tell people some insights about how we achieved them, I think was sort of an interesting, existence proof that no, it can actually be done today, and it can actually be done in a way that's still sort of very, good for business, if you will. And I'm happy to talk a little bit more about this.
Wonderful. I'm sure there'll be people who want to know more. Let me ask Randy. Randy, if information technology equipment really consumes that much, and does it really consume so much energy in a net sense, given that there are actually savings caused by not having to commute as much, not having to get into cars and planes, and what do you know about sort of what the truth here is?
Well, as sort of will sound like a little bit of a strange way of getting back to that question, I wanted to react a little bit to what Luiz said. In some sense, these internet data centers are an example of the industrial infrastructure of the 21st century, right? I mean, it's no surprise that Google's Oregon data center is down the road from a shutdown aluminum smelter, because people don't do that sort of thing today. They do internet data centers. So in some sense, companies like Google have moved us into an industrial scale of computation that is comparable to the largest old-fashioned industries of making aluminum, making steel, and so on, except now we're moving electrons and moving bits. But the thing that's really cool about it is that we can be a lot more efficient and aware of how to do that to achieve these kinds of levels of PUE efficiencies that are 1.2, just 0.2 watts for every watt that goes into running a computer is a pretty amazing thing in terms of energy efficiency. So we could be a lot smarter about how our industry evolves as we go forward. Now, coming back to Shankar's question, this is a very controversial thing. If you look at the data that the consultants have put together, it's sort of a little bit all over the map, but in general, the amount of energy that is consumed by information technology equipment, our home PCs, our handheld phones, the infrastructure, and so on, is about today 2% of the energy footprint of the world. That doesn't seem like a very big number, but the extrapolations forward into, let's say, 2020, that number doubles. So it's one of the areas that's growing the fastest. Especially fast in parts of the world which are not necessarily using the nice hydropower that Google, for example, is using up in the northwest part of the United States. They're using nice, dirty, old-fashioned coal-fired energy plants. So to even say, to factor in the footprint of the information technology equipment, you can't exclude the nature of the electricity and how it is generated when you're thinking about what the real environmental impact of that is. So we have to consider that as well. But 2% to an extrapolation forward of about 4% as you go to 2020. And then the things we've been talking about is energy efficiency in buildings and so on, and in information technology equipment. But there's a much larger sort of set of issues to think about, which is the efficiencies with which we live our lives and do business. What is the energy efficiency gains of being able to participate in a Google project without having to get on an airplane? By doing video conferencing instead of actually, I'm afraid all the Berkeley support staff from the college who are here, we all jumped in our cars individually probably and drove down here. So what was our carbon footprint for this meeting to be in front of you? You really have to start thinking about those things and understanding that, and understanding the way in which information technology can help through remote telepresence, through being able to shift in time the kind of work you do, to make it more efficient. I don't know how many of you are old enough to remember the old Yellow Pages ad of, let your fingers do the walking through the Yellow Pages. That's exactly what Google lets us do. I have a story of, I looked inside my refrigerator one day and one of the shelves had broken. I'm looking at this thing and I'm thinking to myself, God, this refrigerator is like 10 or 15 years old. There's no way I could possibly find that part. I don't even know what number of refrigerator this thing is. I guess I have to buy an entirely new refrigerator. Typical engineering mindset, right? This, sort of $5 part broke. I'm going to buy a new refrigerator. So fortunately, Google existed, And so I went, well, maybe I should just check. It says Westinghouse on the side of the refrigerator. So I'll go to the Westinghouse website. Indeed, you're able to search the Westinghouse website, and they're smart enough to know you don't know what the model number is. So they have the pictures of all the refrigerators. So I can, oh, it's that one. And then from there, they have the exploded CAD-CAM diagram of all the things inside it with the part numbers. So I could actually order and be shipped the next day for like $5 the plastic part, which is the bracket that I needed to replace. I never left my house. Now yeah, it may have come by Federal Express and, a guy in a truck rolling around and all that. But I didn't have to, I don't even know where I would have started to look. What appliance store do you go to try and figure out what this part is? So just to kind of sum up, this is just the beginning of how information technology can dramatically make our society more energy efficient, way beyond our individual use of computers or the energy in our houses, just by the way we live and do business. So I think there's an exciting aspect to that.
Very good.
Shankar, can I jump in there a little bit?
Jump in.
Because, maybe emphasis for the question was there was an article a while back saying how doing a Google search is like boiling a kettle or something, which seemed to be way off base. And the way I look at it is if you do a Google search and you look at the result for 10 or 15 seconds, then your body's consuming more energy than Google is. Your computer is consuming more energy than all the Google servers did. And if you have a light bulb on in the room, then that's also consuming more. So the Google servers are in fourth place for that query.
Very good. Costas, I'd like you to pick up on what Peter talked about. So in zero energy homes, in his earlier comments, zero energy homes, is this, you keep hearing about this, where are we on this? What do we do about residential in addition to commercial?
That's a very interesting question, because the concept of a zero energy home has been discussed for a long time, and people actually can build zero energy homes. They have been building zero energy homes for a long time. A zero energy home that will change the world has to be a zero energy, zero cost home. That means that it shouldn't cost more than the home it replaces. Or at least will even allow you to use the savings in the energy in that equation. Even with that, it should not cost more. And today's technology cannot do it. And the reason today's technology cannot do it is it's not because we don't have the materials to do it. It's not because we don't have the know-how. The cost, I think, is associated with the lack of information. Once you have the information on how a home operates, and once you have built the appropriate models and use the information technologies for that, then you make a giant step in that direction. In the studies that we have done, shows that in order to go to zero energy, the first step that you have to do is to conserve the energy that you consume. And that takes you 80% there. So you have to reduce your consumption by 5 times before you spend your first dollar to generate energy at home, because it's so expensive. And as I tried to show in these few slides, and as I'm sure many people realize, you cannot consume your energy, you cannot reduce your energy consumption by that factor without changing the way you do things. And information technology, information availability, I think is going to be critical there.
So, I've got tons of things to ask them, but I'd like to have you give a chance, if you don't mind. And it's completely unprovoked, so I apologize. But I was having a conversation with Mike Horton, CEO of Crossbow, who's a sensor network company, what sensor networks and energy consumption and homes and all this could do together. Mike, you heard Peter and you heard Costas. You have.
I think that.
Can you use the mic, because I think they're going to record there's a mic out here, and I think it helps the recording function too.
I guess we're doing sensor network work since sensor networks were around and building them and trying to understand for a while, just as a personal hobby, and get asked a question a lot, how can sensor networks help you save energy? And I think one of the key basic fundamental things is occupancy detection. So much of what is on in a building is on just because someone left it on. So we've done a lot of work with passive infrared sensors, which are micro power consumption, can live on batteries for very, very long periods of time, and using passive infrared sensors across a low power wireless sensor network to detect when people are in a facility or not in a facility, and simply turning things off when folks aren't there is a very basic and simple way to save a lot of energy. I think another big thing that at least for the homeowner, and I'm very interested, I wanted to actually ask Professor Spanos a question about how do you cut your energy usage by 80%. So I went through in our house and tried to figure out how to cut our energy consumption down and found that the most effective thing was the thermostat. So, we cut that back by about 4 degrees, and that took about 10% off our energy bill right off the bat by just reducing the heat by 4 degrees. What do you do to get to a 5-to-1 ratio?
Well, 5-to-1 is going to take more than reducing your thermostat. 5-to-1 will probably require a little bit of remodeling too. And it's also going to require a little bit of changing your expectations about what to demand from your home. I was surprised, I shouldn't have been, but I was surprised to find out that architects have been doing studies for a long time now to define what is the ideal environment in a building and in a home. And it turns out that the ideal environment is very subjective. And because occupants live in what architects call the memory space, meaning that once you're used to an environment, you become comfortable with it. I come from Southern Europe, and I came to the United States at a time where air conditioning was not very widespread in Southern Europe. Summers were still 100 degrees, and we're fine. We're used to it. Our expectations were set that way. If I go back to Greece now, of course, everybody has air conditioning, and they wouldn't imagine living in that. So going 5 times, reducing the energy by a factor of 5, will require both the information technology. I really like the idea of detecting presence, because obviously you don't want to air condition a room that nobody occupies or to light a room. But it will also require changing your expectations about what comfort means. And people have proven again and again that people can adapt to environments and be very productive and happy. While saving quite a bit of energy.
I had one more question just to follow back up on the folks that have done and I don't know if some of the folks here have signed up for the Google Smart Meter trial. We tried to sign up, but we weren't allowed onto the trial. I guess it's a fairly narrow set of folks. But what people are averaging 10-15%, what are they finding? What are they doing to get that energy savings? What are the lessons learned from the beta users of that program?
Omar, do you want to take that? It's Omar Khan, one of the engineers on the project.
I'm Omar. I'm actually a Berkeley student too, so this is quite apt. What people often do, I think 2 things to look at in your home that people often think about when they're trying to reduce energy consumption. And one that a lot of people probably in this room don't think so much about, but is sort of your base load. So your home is always using a certain amount of energy, and there's a lot of questions of why that is. And so anecdotally, some people have talked to us and come and said, well, I learned that the computer I always had on was actually using 300 watts all the time. So just things like that. So a lot of people have shut those kinds of things down. And then there's, of course, the large appliances. So you think of old refrigerators, washers, dryers. So sort of changing the timing of when you do those things isn't going to change consumption. But then if you reduce frequency, some people have said that they've reduced frequency, or they've sort of. There's one story of someone who was making toast in their oven. Which he didn't have a toaster, but. If you get a toaster, you're going to see a dramatic reduction when you're using your oven, say, to heat your home or to make toast. So there's all kinds of things that. And one thing I want to point out here is the importance. This feedback is very, very good at motivating people who want to make a difference. And one of the challenges I think we're facing, that we're all going to face, is that everyone in this room might be very interested in reducing power consumption, but a lot of people don't care. And so how you motivate people is a big challenge that we're trying to tackle as well. So it's not just feedback is not going to motivate the person who doesn't care. And so how you generate motivation, how you get social groups involved, how you get larger groups involved is a challenge that we're also trying to tackle.
Now, how are you instrumenting the difference? How is a person knowing that toasting bread in the oven is a bad idea? How did the Google Smart Meter tell them that?
So first of all, we're only instrumenting the whole home. So the smart meter, the power meters is the sort of the name of the project and the technology, and it will only show you sort of the bigger things and sort of your base load. So you can't get very detailed measurements. But if I show you this graph, if I showed everyone a graph on here of someone's home, you'd all be like, oh, that looks kind of boring. It's not that interesting. But when it's your home, you know everything about it. You can like see that little spike. Oh, that's when we were watching the TV, or when we turn on the dryer for 10 minutes. People know what the graph says, and they will tell you stories until the end of time unless you extract yourself from them, because it's a very, very personal thing. So so I would say that people have been very just willing to interpret this data and have been very good at it.
Okay, can you use the mic? Please jump up. Yeah.
One problem I see is that home energy price is actually quite low, right? So it seems like the only way you can convince people to use your solution is to actually lower the price of your solution, right? In order to motivate them to use it. Otherwise, how do you
Costas. So this price as a signal is also okay. Can you actually broaden the question? Is price the only good signal?
So I wasn't sure. You mean the cost of the solution or the cost of energy?
He's saying the cost of energy is already
yes,
low.
You're right. The cost of energy is low. The cost of energy is probably going up, and it depends where you live too, right? The cost of energy in New York City is ridiculous. The cost of energy in California is somewhat high. The cost of energy in a place like Toronto, Canada, is very, very low. So energy prices are not necessarily a motivator. But one person we talked to here, I'll just give another example. We have this notion of your sort of score relative to other people in like who are using the system. And I was talking to this one woman last night, and she was saying how she saw that she was like only better than say like 40% of the other users in the trial, and this drove her insane. And so she had to reduce her consumption to do better. And it was nothing about price. So what the motivators are and what are the incentives that you can align with people, it's going to be a challenge to identify what works with what people.
By the way, what you talked about is sometimes referred to as a Prius effect, or Pius effect, if you like it better. Costas,
if I may, the discussion about price kind of assumes that people have to give up something to save energy. And for the first 20% or so, usually they have to give up nothing. It means that you do not have to illuminate a room when you're not there. It means that you have to turn off the air conditioning when you're not at home. Okay, so I think metering and visibility helps you do that without really any cost to your well-being. It is beyond that point that price that's playing a role.
Peter, sensor networks. Just to paraphrase the question, so you can tell a lot about what's going on if you know what's in this building, and certainly I know of studies of dorm rooms in dorm floors in Cornell being instrumented at the subfloor level and so on. So what all should we be measuring?
Everything. All the world's information, and we should be keeping track of all of it.
I figured you'd say that.
No, I think there's a lot we need to know. I was just at Santa Cruz last week talking to some of the statisticians there that work on climate modeling, and they say, we can't make good predictions. We know you can draw these graphs, and as CO2 goes up, temperature is going to go up. But we can't tell you there's going to be this amount of drought in this particular area because they just don't have the data. And so we need better models, and we need both better data for the models. We need to be able to collect what's the temperature like, what's the humidity, and all these other things in lots of different places. And then we need the computing power to be able to deal with those models. And some of this is going to be driven by big science and governments and so on, but I think a lot of it can be driven by citizen scientists, right? So if we make a thermometer be a standard peripheral on a cell phone, then everybody can be out gathering that data. And as people are motivated to do so, they can add extra peripherals and gather more data and start sharing it and start participating.
Hi, Fred from UC Berkeley. So I actually have a question about not only what to measure, but also where to measure. So one thing that we're seeing about measuring electricity is that from the very sort of endpoints of the load tree is, the AC outlets. So you can measure exactly what one appliance uses. And the other approach is to measure the entire house or the entire building with some sort of, current transformer, some sort of clamp-on sensor. But they all have their problems, right? You do not have the money to measure every single thing that's in a building. at the outlet level, nor do you have the visibility using just one sensor at the house. So do you have some idea of what's the sweet spot in measurement? Do you want to basically go with the individual measurement at the appliance, or sort of play some tricks with load disaggregation at the very top? What's your view as the best approach to this visibility versus cost, I guess?
I was going to jump in and just to some extent repeat what was said earlier. It's always tempting and very often the right thing to do to measure everything, right? At some point, it's economically sort of not advantageous. I think that what was said earlier, I really believe that it's true in that if you have good enough time granularity for your measurements for the whole house, it's fairly remarkable how much you can tell. And really, if you consider the fact that most of the gains are going to come from big ticket items, those are guaranteed to show up. So as a first order approximation, the whole house sort of approach seems personally to me very promising in being kind of very much at that sweet spot. And in that case, the main thing you need to do is actually to make sure that you're not measuring that as a daily average. In that case, you really don't have enough, right? Or maybe an hourly might even not be sort of good enough, right? But if you begin to have things that are sort of at the minute granularity, I think it's remarkable how much you actually know about what's happening. And in particular, the big ticket items are knocked off sort of relatively quickly in that sense.
So for the Google Power Meter, are you guys doing sort of automatic disaggregation, or is this relying on the user to spot which part of it is what?
Well, just for brevity, I'll reply for my colleagues here. No, the user's eyes are disaggregating things at this point.
But let me ask you the opposite question, Luiz. So, there's a lot of activity on sort of low power technologies for processors, laptops, mobile devices. But now from the micro to the macro, what are your views about sort of going from what we're doing for small devices, and so doing nothing better for small devices, to bigger things like data centers and so on?
Yeah, that's an interesting sort of segue if you want to move in sort of from sort of home appliances all the way to sort of things like data centers. And sort of very briefly, people have been thinking about energy efficiency of computing for a very long time. It was not just data centers that got them to sort of begin worrying about this, right? But the kinds of solutions we've come up with are, reflective of the kinds of problems we're trying to solve at the time. So the way I look at things, big jumps in terms of the way we solved energy efficiency issues occurred maybe in the 90s or so with sort of mobile devices and the needs of mobile devices and portable devices, right? And things like sensor networks, for example. And the characteristics of those devices are so that, they have to be untethered. So you have to worry about battery life. Maybe you have to worry about sort of your cell phone being too warm in your hand or something, right? But that's what drove sort of innovation, maybe sort of for most of the 90s, right? And then, around 2000, 2002 or so, then there was another big research factor, which is temperature, right, for microprocessors in particular, not just for all electronics, but really just for microprocessors. Important to remember that. And that drove a bunch of new technologies for low power sort of electronics that really addressed peak shaving of power for the objective of controlling temperature in microprocessors. So what you see is that the solutions that appear, first of all, have only appeared for microprocessors. The rest of the box sort of hasn't really benefited from it because they didn't have the severe temperature problems that microprocessors had. But also, they didn't really worry about energy. They just worry about temperature, which is a function of sort of power density and things like that. Now, if you begin to think about the data centers, and that connects to the energy proportional computing sort of thing we've been talking about, has been mentioned earlier. It's a great start to be able to have devices that when they're truly doing nothing, like your cell phone right now, hopefully, or your laptop, hopefully as well, because otherwise this panel wouldn't be that interesting. Then they're consuming kind of almost zero power. And we already know how to do that relatively well. And that's going to work well for maybe a lot of sensor networks of applications as well. But for a lot of other computing, and especially as you go sort of to the cloud computing infrastructure, which, as Randy mentioned, is sort of growing in importance in terms of footprint, they are not like that. They are not devices that are just on and off, right? They are often just sort of 10% utilized, 20% utilized, 30% utilized, right? Now, until now, we haven't had the motivation to build devices that are very energy efficient in that range, because we've sort of been riding these other research vectors from sort of managing temperature in microprocessors and making sure that energy is well used on devices that are mostly idle, right? So there's a new interest right now in sort of trying to make sure that we capture that range of the utilization spectrum well. The things that are kind of working a little bit, they're not working very hard, or they're not sort of not working at all, but they're doing some work for you. And that's what this energy proportional computing idea sort of comes about. And what we're trying to do is sort of to make sure that people pay attention to this, because when you actually look at it, there's a ridiculous amount of low-hanging fruit there. I mean, it's typically one of these situations where we just have been paying no attention whatsoever to that. So, and that's why servers are so incredibly inefficient these days when you're running them at sort of 30, 40% or so. And the nice thing, though, is that once you actually do that, the technology you develop for that are not just useful for servers, they're useful for everything, right? They'll be actually beneficial to your mobile devices as well, right? Even if you didn't begin thinking about that as being sort of the main sort of issue. So there's lots of different ways to sort of think about energy efficiency research. The usage mode can drive the kinds of solutions you have, right? And that's sort of one of the things we're learning right now when we're beginning to see how to operate really big data centers and try to make sure that that's been done in the most efficient way.
Could I make just a follow-on comment? I know we want people to ask questions too. One of the things that I find to be really interesting is this whole notion of energy proportionality. When you start studying all the elements of the energy system, you look at the HVAC systems, the power distribution systems, whether it's at the board level or for an entire building. You look at transformers and generators that are out in the distribution and transmission infrastructure. None of them are energy proportional. They're all designed to be most efficient when they are highly utilized. So now when you think about the advances we're doing at the computer node level of having, if we can reach that dream of being able to have a nice scale from when they're highly used to when they're not very used of harnessing reductions in energy demand, what about all the stuff that's feeding them? They don't work like that. They work like, the original charts that I actually, Costas stole it from me and I stole it from him, by the way, those charts that we're showing. But those were for computers, and it's the exact same issue for all of the physical systems around us. They're all optimized to work at high levels of utilization. So if you want to be able to slide everything down and harness energy advantages from doing it, it doesn't stop at the computer. It goes all the way through the energy system.
Andy Cho, Cal alumni. First of all, I'd just like to thank you guys for coming out. I actually live in a neighborhood where all of the homes have PV systems. So I can speak to a lot of the positive feedback that goes around. I'm kind of excited about the fact of competing with some of the other homes, but a lot of it does come along. There's that monetary factor. I'm actually generating more than I'm consuming, and a lot of that is because of the reports that I'm watching. Along with that, because there's actually a bill that's going through the California Congress about requiring builders to provide PV systems as an option. I know that's going through, and they're trying to see if that can pass. How do you guys feel about legislation as a way of pushing this kind of energy movement forward?
Are you taking it, Costas?
Yeah, specifically on the PV systems, the way the technology exists today, unfortunately, they are so expensive that you have to use either the carrot or a stick to make it happen. Carrot, of course, is to give enough incentives. Stick is to mandate it. You probably have a PV system, and you probably know that even though you feel very good about it, you're not going to get your money back in terms of energy.
Right. The ROI is obviously lost.
The ROI is lost, and people are working very hard on the technology of that. They try to use materials radically different than silicon, because silicon is extremely expensive, semiconductor-grade silicon. But unless we find a way to reduce its cost by maybe a factor of 5, I don't think PVs are going to compete with today's energy prices. Maybe 20 years from now, they will be closer.
Let me jump in about the regulation story. So there was a bill. There was a bill in the legislature last year which said zero energy homes by 2030, I think, or 2025 or something like that. But there's a rider in this bill which says unless PV technology is mature, in which case So there's a little bit of an out on it. But what's driving the legislation in California is really this AB 32, which is a cap on the greenhouse gas emissions, which Governor Schwarzenegger announced. And really the role, so the bigger question, and I'm now, is really the role of regulation. So I think the reason that so I was party to some of the California Senate and Assembly discussion. I think that the good thing is in California there's a sense that you cannot sort of have punitive legislation that makes you spend what do you spend in your neighborhood to put in PV to get to those zero energy. I think what I've heard Steve Chu say is actually a little more pessimistic than what Costas says. The factor of 10 is really what's needed to get closer to the zero cost. And but they're pretty upstream technologies. If you really want them, there's go. So I'm going to stay out.
No, it's okay. Don't stay out. I mean, this is very useful. But I wanted to say, because I was asked before about the zero energy home, and I did not come out enthusiastic about it. There is nothing wrong about the zero energy home, but the zero energy home is not fundamentally better than the zero energy community. And a zero energy community is much more feasible because all these renewables can be produced at low cost at scale. So zero energy home sounds good, but zero energy community is probably the way to go.
Yeah, and then when you look at communities, of course, I mean, the reason you'd be able to actually do some of the investments in sort of higher volume that sort of amortize costs, right? For example, if you just thinking about solar, for example, Google's been involved in some projects to sort of cheapen the costs of some energy generation techniques. And right now we're sort of, putting a sort of relatively big bet on things like solar thermal, not photovoltaics, for example, which as far as sort of harnessing sort of sun sort of energy directly seems to be much more promising. But it is less likely, and you know better, Costas, that is something that you would have in your home, but more likely that you have sort of at a coarser granularity.
If one were to slice it, I think energy efficiency has to happen at home. Energy renewable production probably needs to happen at a bigger scale to make sense.
Adam.
Yeah, so I was wondering.
Identify yourself.
Oh yeah, sorry. I'm Adam Cataldo. I work at Agilent Technologies in the research labs over there, and just interested in this energy problem. We're a measurement company, so I'm interested in what kind of opportunities there might be for us in this space. But specifically with the data center question, one thing I'm wondering is how does the energy consumption of running your server or using your cell phone for that matter compare to the energy used in manufacturing it? I'm just thinking that I get a new cell phone every year, I get a new computer maybe every 2 years, and that manufacturing energy might be, sort of worse because maybe it's made in a part of the world where they burn a lot of coal and, it may be less clean than the energy consumption that's right next to the hydroelectric power plant or whatever.
Who's going to take life cycle costs?
Well, when it comes to semiconductor production, studies have been done to see how much of the energy goes into production, how much the system burns when it's running. Of course, it depends on the product. Some products are meant to consume very little energy and use very infrequently. But if you use a high-power microprocessor that is used, well, then only a trivial portion of the energy goes to producing it. Most of it goes to operate it.
Does that include the cost of the casing and everything else though?
Yeah, it does. But of course, you can find counterexamples because some electronics are meant to be used very, very little or with very little power. But semiconductor manufacturing has improved in terms of energy and in terms of environmental footprint quite a bit.
Another issue that sort of from an environmental standpoint that we haven't talked about that's really relevant and it's going to be sort of in our tip of our tongues sort of everywhere very soon is water, right? Mm-hmm. And that's sort of interesting because a lot of the solutions we have, for example, to run data centers very efficiently is to use things like evaporative cooling, which use water. So in principle, you think, well, maybe sort of you're solving one problem, sort of creating another one, right? And that to tie again to something that was said earlier, if you don't trace the electron from its source, you actually may sort of miss the big picture. It turns out that if you actually don't use evaporative cooling and you use mechanical chillers, right, that don't really sort of use any significant amount of water, in the entire food chain of the electron, you actually end up being worse off because you use so much more energy. and the production of that energy actually uses a tremendous amount of water, right? That the relatively small amount of water that's dissipated on evaporative cooling ends up sort of by and large sort of being a win, right? So this is one of those situations where, you know, if you sort of look at the small part of the problem, you may actually react exactly in the wrong way, even if you had sort of best of intentions.
Adam, by the way, thanks for asking your question, because after Omar got up there and talked, I was thinking maybe I should have gotten a new refrigerator. You reminded me of, you know, maybe the total life cycle cost. It's good that I'm still running a 20-year-old refrigerator.
Very good.
Thank you.
Tony Chen, I'm Cal alumni. And so one question I have is that energy efficiency is not just about like, you know, how you can save on energy, right? It can also be the other way around, like, you know, how can you recycle the energy, right? For example, the Google data center generates a lot of heat, right? Like, you know, do you guys do anything, or like, you know, is there any research being done that you can, that for example, like, you know, pipe the heat into the office next door, right?
Yeah, so this may be one of the few criteria upon which a data center is worse than an aluminum smelter, I guess. In that, you know, machines, and in particular the heat that's generated in the data center is really low quality heat, right? It's very low temperature, and you know, if you know, thermodynamics tells us that the amount of sort of actual useful work you can get from low quality heat is really little. So we're very limited in that sense. There's a couple of things we could try to do. One of them is convince the whole industry to allow their electronics to run at sort of 300 degrees Celsius or something like that, right? In which case our wasted heat will be sort of super good. And the higher the better. You know, unlikely that this will be an end-to-end win, but, you know, it's worth a shot. The other thing you could do, I mean, if you're very close to large communities, maybe some of this even low-quality heat can be used, right, to be piped into homes and things like that, etc. Probably wouldn't be enough to, you know, if the place is sort of very cold, but, you know, that's something that could be explored. One thing that some folks have done in some areas where they generated relatively low-quality heat has been use it for industries that sort of have fermentation needs, right? So, you know, if you want to make beer or yogurt, for example, low quality
I think maybe
heat
biofuels. You should say biofuels.
There you go, biofuels. So, you know, you know, so it's not an impossibility, but certainly your options are much fewer than other industries that actually generate much better quality heat.
So let me support Luiz. You know, so Carnot efficiency is 1 minus T1 over T2. The problem is this T1 over T2 is so close to 1 because of the temperature. But you know, the bigger question, I think 55% of the energy that we produce in this country is wasted as heat. 55%. And the bulk of that, of course, is in the power plants where you do generation. And there, this question of what you do with thermoelectrics, new materials. I mean, thermoelectrics is a solution that we've touted for 20 years, but hasn't sort of fully arrived. And here is 55% of our energy, input energy. So that I think is a big ticket item.
I just wanted to say one thing we did do was make a survey of failures of disk drives. I think it was the largest survey that had been done, and we determined that you can actually run them a little bit hotter than the manufacturer's recommendations, so we can turn up the temperature a little bit and not worry that much about the cooling costs.
We've actually done that, and it saved us a tremendous amount in cooling. Yeah.
All right, thank you.
Costas, did you want to say something?
No, I just want to say that when it comes to waste heat, in places like Denmark, for example, they use coal-fired plants that they don't have very good efficiency, but they use the waste heat from these plants to distribute hot water to communities. And the overall efficiency is about 100%, right? It's very close to that. So there are opportunities, but not with low temperature heat, unfortunately.
Hi, Yash. I'm hesitant to say which company I'm from, but I guess I'll say it, Intel, because my question deals with semiconductor manufacturing. And I know, Professor Spanos, you've done a lot of work on that side. Here's a question. Back in Berkeley, you know, in the micro lab, for instance, we would waste tons and tons of water, pure DI water, right, just to clean a few 4-inch wafers. And now that I'm in industry, I realize that the problem is 10 times worse. I used to feel guilty about it back in the day, But now it's tremendously wasteful, it seems. So I'm wondering, are there any technologies out there that, that can make us feel less guilty about this? And it's important, right? Because it's like day in, day out, I go to work and it's like, wow, I'm like the worst person, on the planet because I enabled this technology. The other question is, I just, as a follow-up, and then I'll sit down, you mentioned power distribution, 55% wastage. That is so true. And I think there's a lot of effort now, or should be, in localizing power generation. So what can we do to really have literally thousands of power distribution systems, maybe even, in area the size of Bay Area, right? So can we get localized energy centers and then distributed locally? So
I'm sorry, thousands of what system?
Power generation centers in the
distributed
in an area the size of Bay Area, for instance.
Okay.
Would that help?
Okay, let me take your first questions, which is electronics manufacturing. Back in the early 90s, when there was quite a bit of pressure about the ozone hole, you remember that? Mm-hmm. There was quite a bit of pressure on semiconductor manufacturing technologies to clean up their act in terms of the solvents that they put in the air. And the industry has responded, and in fact, now they're extremely clean on that. I suspect that when appropriate pressure, either legislative or price pressure, applies to DI water usage, you will see the industry becoming much better. Just to give you an example, which is not semiconductor manufacturing, but PV manufacturing. Most people do not know that PVs that were built 10 years ago, the energy consumption and the carbon footprint in building them was so bad that it took about 10 years of operation before they redeemed themselves. Now this time has been reduced to about 6 months. So the industry has been driving in that direction. So there are opportunities, of course. Now, to address your question about distributed energy generation, and this is something that I think was reflected quite a bit. Many of these things are built to operate at scale, and they are built to operate at 100%. Randy has complained about transformers and distribution, that they are built to work at 100% only. Well, turbines and generators are really built to operate at 100%, and it's a big waste if they do not. In that regard, I do not really believe that distributed generation is going to be the solution, because even though you waste a little bit of power over the grid, you make it up with the efficiency of a big system. The only natural distributed generator is a PV, or maybe a thermoelectric or solar thermal at the scale of a home. And you'll have to wait until the price goes down before that makes sense.
Gotcha. Randy, did you want to chime in on that?
Well, I think there does require some technological breakthroughs on having efficient, smaller generation technology, because there is an economy of scale and things are designed to operate efficiently at large scale. So, but you talk to people who know about things like gas turbine generators, and there are examples of much smaller deployments that may not be at the level of the home, but might be appropriate for a facility like the Googleplex, for example. So they're at least for large, university campuses or industrial campuses or things like that, it can make sense to have, which would be the equivalent of a neighborhood, hundreds of homes rather than the entire Bay Area on one distribution system. There's a whole other dimension to this, which is our current regulatory environment does not allow us to do stuff, limits the ability to truly share energy amongst a community. You can operate your own, in fact, you're sometimes required to, universities are required to run cogeneration facilities and things of that nature. But if you really wanted to enable, I think, the kind of distributed generation that you're talking about to drive the technological developments, to drive the manufacturers to come up with a more scalable set of technologies, there has to be a way in which energy is shared, or there's a way to build a more localized marketplace. And that requires some regulatory involvement in order to open that up. Because today everything is geared towards the large-scale utilities as being the providers of energy and delivering it to you. And the entire industry supports that particular model. So that has to be addressed as well as the technology.
Great. Jeff Walls with Google. First off, I'd like to congratulate Berkeley for taking on this problem we have with energy. And I had a question on education. When I was studying electrical engineering a long time ago, I took a course called Power Systems. And I was the last class to take that course because they decided that the problem had been solved, that we no longer had to worry about that stuff. And the professor was about 90, and I think he was retiring. So, the funny thing, and I was at MIT a few months ago, and they said, yeah, we have that problem too. No one knows this stuff anymore. So I'm wondering, what is Berkeley doing? It seems like we've lost a generation there. Who's teaching the students, and what kind of education, what kind of courses is it? It sounds like we're getting onto the research goals here, but who's learning the new tools, the new techniques, and that kind of thing?
All right, great question. All right, so, panel, you got it.
I think the professors on the panel should try and take a stab at that particular question. So, taking the observation of fellow colleagues who are or were department chairs up here, really being
you're responsible for what you said.
I have to say that being in the San Francisco Bay Area, both Stanford and Berkeley, we were very early in the days of semiconductors. And if you were to go visit Berkeley or I imagine Stanford in 1950s, the buildings were filled of power system engineers. And the hot thing to do was to bring in young, new faculty members who knew about semiconductors. And within a generation, the balance went entirely the other way, that we have lots and lots of people like Costas over here who are experts in semiconductor technologies, even down to the level of our last remaining power systems faculty member really knows about things that are, integrated power supplies and things at that sort of medium scale level. So it's true that at places like Berkeley, Stanford, and MIT, surprisingly, because we've all been on the forefront of the semiconductor revolution, the knowledge of power systems on the macro scale has been lost. It's interesting that I'm sure there are many people in the room who've gone to Big Ten schools, Midwestern schools. Those kind of places still have power system engineers, by the way. But maybe this isn't such a disadvantage because now there's an opportunity to really take a new 21st century view, an information-centered view of what power systems, from a scalable view of power systems, from the small to the large, aware of the kinds of applications like data centers and so on. This is not your mother or father's power system that we're looking at for the 21st century. It's a very different kind of beast. I think it's a huge challenge for the universities to really think through what is the educational basis of that. At Berkeley, our colleague, actually, Seth Sanders, who isn't here today, pioneered and pushed forward this idea of an interdisciplinary energy course that we're teaching this semester, where we've got people who know about buildings and know about or trying to know something about distribution systems, all the way through to the turbines, to the mathematics of energy markets. We're trying to figure out how to integrate all of that new knowledge into a coherent set of curriculum for what graduate students should know about energy systems. And I think that's just the beginning of a very important set of activities that have to go on to understand what the educational component of that is.
Good.
There's not much to add. I'm not going to make any apologies for not having a power system engineer at Berkeley. The decision was made long before my time, but I think it was the right decision at the time because information technology was the way to go. And now puts us in a position that to use really 21st century tools to this problem and to look at this problem differently.
So let me take one more question from the audience, and then I've got a question for each of you. So please.
Okay. It's kind of maybe a crazier question than what some of the other people had asked.
Please identify yourself.
Yeah, my name is Rishi Chopra. As an EECS graduate. Is there any interdisciplinary work that's being done between engineering departments? Because I know that this problem of managing heat and heat loss is not uncommon across disciplines. Like you're saying, 50% of the energy is just wasted to heat. I was thinking of one example where dry fuel storage for nuclear power plants. If you have a spent nuclear fuel rod, it's very hot. It has to sit. It has to be safe, but it needs to be cooled too. But all those things are cooled passively with concrete. So, is there any type of research that's being done, or are you aware of any type of collaboration?
So, can I do this? I think part of what we're talking here is that we are gearing up at Berkeley to do something substantive in the area of sort of addressing two pieces, certainly energy efficiencies, but also new generation technologies with a focus certainly on buildings. Transportation, I think this biofuel story is often running at Berkeley, and that's in pretty good shape. The other part is about industry, and that includes cement, glass, even these aluminum smelters. 3% of the carbon dioxide that's produced is in cement, and so green cements and all of that are also a big agenda item. The work is wonderful because, even though, one thing I'd like to add to what Randy said is, even though we sort of downscaled our energy efforts, luckily for us, we had LBL next door, the Department of Energy lab, which really kept through this period when we downscaled our own efforts. Fantastic material science division, which we've been thinking about novel materials, buildings, energy efficiency and technologies division, and a lot of the people, including current science advisor to the president, John Holdren, came out of a lot of these programs. So now I think the strategy is to gear up. And Citrus, I think, was sort of an example for us of a multidisciplinary initiative which pulled in social legal, the so-called ELSI, economic, legal, social implications of the technology. I think we're going to try to do the same thing for energy. Exactly how we'll do it, we'll reveal before April 1, 2010. How's that? To match Luiz's. And it will, a lot of it is resurgence. I have to share with Randy and Costas, it's not so bad that we really sort of skipped, we brought to a termination one set of technologies for energy. And now I think there's going to be a new set of things. The Randy and Costas talking about an internet-like model. So Randy's phrase is from a industrial age infrastructure for power to a internet-like infrastructure for power and energy and sort of materials. We've invested 10 years in nanotechnology, nanoscience, nanotechnologies. And so exactly how we're going to use this, there's talk not of using silicon, but ferrites and sulfides and so on to make, rust, making PV out of rust. So those are the kinds of things that you can do if you're starting with a clean slate. And that's, so I think that, so you'll see us gearing up to do something. And it'll be pretty, it's LBL Berkeley. So, Steve Chu taught me one thing. As soon as I started, he said, Berkeley means University of California, Berkeley plus LBL. And he really lived this and certainly made me a believer. And that's sort of how we're going to be sort of presenting our energy strategy. So I'd like to ask each one of you in turn if there's one thing you would like to give as advice to President Obama about what he should do. And there's only one. So I think, should we start with you, Luiz, and just sort of work our way down?
No, I was hoping you were going to start at the other end.
Oh, all right. If you prefer.
This is easy. You're the first one.
Everybody else will have to say something different. How's that? Would you rather? Okay. Would you rather?
Well, I guess I'll volunteer one thing, I suppose. You have to look at the big ticket items, right? So energy production and transportation, right? Sort of, a general focus on these areas seems to be a big deal, right? And my understanding of what I hear from the current administration seems to be that they sort of understand that information technology is the enabling sort of, I don't know if the key enabling, but certainly one of the top key enabling technologies for further efficiencies on both of these industrial sort of areas. So if it's indeed the case that, they are sort of going to be focusing a lot on that and sort of understanding that, information technology is the key component sort of in sort of unlocking the potential efficiencies in those solutions, that'll be it, sort of keep going in that direction.
Super. Randy.
Well, I think my favorite thing would be to push for a carbon tax. I think really we need the economic incentives to get people to understand the true cost of energy and to facilitate the investment in the technologies, the driving forward with new, more efficient technologies. Because right now, as several of you have said during the last hour, energy is really cheap. Well, is it really cheap? Are we really cost accounting for all the implications of its generation, distribution, and usage? Can we have a way of recapturing that and use that as an economic incentive for building more efficient systems and for really triggering the development of new technologies? I think that it's going to take a tremendous amount of political will to do that, because all the standard answers are, we can't afford it, we're not going to be competitive, it's going to cost us too much, it'll put people out of work, et cetera, but unless we do that, we can't move forward in really getting the investment in these new technologies. Europe is doing it, why can't we?
Yeah, that was going to be my question if you had started. So, giving me another 5 minutes, I was going to answer exactly that.
Yeah. Peter.
And I come after Randy rather than before, so I get that advantage. So that's certainly a good one. And I guess the way I look at it is you can use that kind of advice to simultaneously solve energy, climate, and the financial situation, right? Because you can form a new industry, and we can be at the forefront of that industry. And I think an important way to look at it is to say it's not that capitalism is broken, it's that we were just doing it wrong. And you have to internalize the externalities or else everybody cheats. And if we get that out of the system and build a system where we're trying to optimize the right thing rather than the wrong thing, then we get back on track.
Very good.
Agreed.
Costas. I was going to say you had the last word, but we're going to give it back to Luiz for the last word.
Wrapped around.
But you have to say something new, right? All right. I mean, I think Randy captured it in the sense that you need the carrot and the stick. But I want to say that, again, having come to this country a long time ago, but I still can see it, with some clinical distance, we have been spoiled for generations with abundant cheap energy. And we have built our lives around that model. We commute long distances. We live in big houses. We do not mind if the air conditioning is running or if the heat is running when nobody's there. You can mitigate some of that by, of course, a carbon tax by pricing everything. But the shock to the economy will be huge if we really try to price that out. And I think that early education, breaking us out of this mold, I don't know how to do it, but I think that will be a very high priority to get us into a mindset that we care. And I don't think we're there yet.
Okay, Luiz. You have the last, but this is going to be real advice. I'm going to personally relay it. So,
wow. Yeah, I think you should just take Randy with you and do whatever he says.
All right. Thank you all very much. Before I I think the highlight of these evenings is a chance to sort of have a little bit of schmoozing. I'd like to thank the panel. I'd like to plug the poster folks who, I'd like to just sort of tell you who they are and what the posters are, so that while you do the networking and partake of the food and drinks and the wonderful hospitality of our hosts, I'd like to say there's, out here is coupling renewable energies with flexible electricity demand, Pediakos, Ken Wang, and Thomas Dickhoff here. Climate Navigator with Nina. Nina, actually, can you folks identify yourselves, the first three? Okay, good. And then Climate Navigator, this is an attempt at really trying to measure carbon footprint and this is Nina, Gary Baldwin here, and Mark Huberty. And then silicon carbide, harsh sensors for harsh environments. Debbie Sineski, low temperature solar thermal conversion as controllable generation energy storage. Mike Key, low-cal architectures with distributed energy generation and control. Evan Ritzel, there you are. And I think Fred, what's your poster called? Yeah, so it's wireless sensor networks for building efficiency with David Collar. That's the poster out here. And finally, before I'd like to thank the panel, but I'd like to thank our hosts and especially Sanita and her staff for pulling this event together. And I invite you all to sort of enjoy the rest of the evening in each other's company. And thank you, panelists.